All right, so Happy New Year and Merry Christmas. Until now, we have talked about uh, optimization approach to solving approximation algorithm. So we have used lots of STP relaxations, LP relaxations, but sometimes we could use some other paradigms, such as, for example, primal draw approach, such as just purely combinatorics, and it is related to probabilistic approaches, which is very, very beautiful and natural, more natural than using some LP or STP packages. So sometimes we don't need LP and STP solvers. And for example, in Karger min cut, in Karger minimum cut, as you know, it is a very popular approach. Still, after 30 years, it is very popular. Many articles in 2020, 2021 still use that in some part of it in their article, in their algorithm. So, because it's very natural. So the algorithm of Karger is very simple. We just pick a random edge, U and V, and then we contract it. So we want to output the surviving edges as main cut, because sometimes it goes wrong and it is not your main cut. But because at the end of the day we have a value for that cut after several times, that's why it's a randomized algorithm. After several times with high probability, we get what we want. We get mean cut. Of course, this approach, it can also be used for K-cut, because we can stop before K edges are left and K parts are left. And so today I want to just analyze this beautiful algorithm mathematically. So we fix some mean cut S and S bar. So going from S to S bar. So we say this edge, this red edge, is safe if it doesn't, if it is not one of the crossing edges. Or for example, this edge, because it doesn't cross from S to S bar. So we can calculate the probability that the process that I said, just contraction, pick an edge randomly, uniformly random, and then contract it. So the probability that this process output the correct one, given that edges from S to S bar, so this is just the probability that we can define KCI to be the random edge. The event that random edge of the ith iteration is not a S and S bar cut edge. So it's not a crossing edge. So what is the event? We say, for example, KC1. But KC1 is at first iteration. KC2 is at second iteration. For example, the event that the random edge that at the second iteration is not a crossing edge. And so on for all events that happens. So we want to calculate this probability. And what we can do is just saying that this is just probability of KC1 times probability of other events conditioned on KC1 using simple probability. And recursively, we can go on and say, okay, this is the probability of KC2 conditioned on KC1. times probability of intersection I from 3 instead of 2, from 3 to n minus 2. And this goes forever. Kisi I conditioned on what we are Kisi 1 and Kisi 2. And when you multiply all these things, you will see that this becomes the product of I from 1 to n minus 2, the probability of event Kisi I conditioned of intersection of several events, j from 1 to I minus 1, and this is the probability, is the product of probabilities. Now ith iteration, I mean the ith min cut, it's avoiding the ith iteration, that it's avoiding the min cut, because otherwise that will not be the optimum. So conditioned on given that the first I minus 1th iterations avoid min cut. And we suppose that the min cut is the value of min cut, because it has a value, is just k. And we know that, for example, you want to calculate the first event, probability of Kisi 1. So we know that when you go from S to S bar, okay, there are some edges. There are k edges. For example, these are k. There are k edges. So among all edges, we have m edges. If you just forget to use those k edges that are going cross, then this is a probability of Kisi 1, because m minus k edges are very good edges. We are very lucky to use those m minus 1k edges. These are good edges. And total edges are m, so this is the probability of Kisi 1. But I want to show you that this is greater than 1 minus 2 over n. This is already 1 minus k over m. This is 1 minus k over m. So I just want to use the fact that if you just, if two times number of edges is just the sum of degrees of v. So the sum of degrees of v for all vertices, so it becomes, so each vertex is we know that degree of each vertex is greater than k, greater than minimum cut. For example, this is one vertex, so the degree of this is greater than minimum cut, because this could be S, this could be S bar. So degree of V is equal to K plus K plus K, and we have n of these, so this becomes nk. So this becomes greater than equal to nk. And from this, we can say that k over m is less than equal to 2 over n. So now back to what we want. So 2 over n is now replaced by k over m. And if you just calculate all of these, so the probability of mean cut is output. As I said, that becomes greater than product of I from 1 to n minus 2 times. So we are calculating those things. So you will see that this becomes the product of y n minus I plus 1. And this becomes n minus 2 over n. n minus 3 over n minus 1, n minus 4 over n minus 2, and all of these using the telescopic things, you can use 2 n minus 1, which is 1 over n choose 2, and you can use it the lowest things. You can think it is at least 1 over n2. So the probability is at least 1 over n2, which is because you have the capability of doing computation. So after some time, you will have that mean cut because you're measuring all mean cuts. And we know, and we use just the fact that probability of KC2 condition and KC1 is greater than 1 minus 2 over n minus 1. And we have just written this as n minus 1, n minus 3. The same things, probability of KC3 condition and KC1 intersection with KC2 is greater than equal to 1 minus 2 divided by n minus 2. And the same thing happens for probability of KCI conditioned on j from 1 to I minus 1, KCJ, which is greater than 1 minus 2 over n minus I plus 1. And that's it. That's the analysis of using probability to analyze what is the probability that mean cut is your output. You may say that if you increase the number of vertices, n, which is the input size, then this probability is very, very slow, very, very, very low. And of course, Karger modified this algorithm, and many people are still using this. And for the mean k-cut, for example, you contract it until only 3 clusters remains. So this is one set of vertices, this is another set of vertices. So for example, this is a k-cut problem for k equal to 3 because we have 3 different clusters. So we want to minimize the weights of crossing edges. And so we can also use it for k-cut problem. So the Karger's algorithm can also be used for k-cut. And nowadays, for example, Chandra Chekuri, I will explain one day that he used a Steiner k-cut problem, and also of course using those tree packing, he used an algorithm to calculate to find the k-cut. Also, recently, for example, after 2018, many people such as Anupam Gupta started to use some new ideas. For example, also some people use, for example, parameterization algorithm, fixed parameter tractability. And for example, if you say that we have your cut size is just, if you restrict it to some specific cut size, then you can use all ideas from parameterization, branching, kernelization, and all of those techniques that we use in parameterization to just increase to have a better algorithm. And recently many people, many researchers are focusing on parameterization methods because they think they should understand what is the hardness, what is the problem that they cannot improve. So we want to see if we put some structure, some combinatorial structure on that, maybe it could become a more flexible algorithm so that it could be more tractable in order to improve it. Otherwise, we are still almost the same things as those Karger-Stein algorithms. And so in the next lecture, I will talk about primal dual algorithm. For example, we will show you that, for example, you know that the SAT is at least as hard as 3 SAT. And this is this could be graph coloring. This could be vertex cover. That's why vertex cover is very important. Because if you solve it, then you can understand many other problems as well. Also, mean Steiner tree is important. Steiner tree, Steiner group, all of these things. And for 3 SAT, for 3 SAT, we have graph coloring and vertex cover and max cut. Max cut is also dual of those mean K clustering. And the max cut is very interesting. About the vertex cover, you can also say that it is as hard as independent set. You can say vertex cover, set cover. Set cover is really important because it's Karp's 21st NP complete problem. It's one of those 21st NP complete problems. Also, the mean Steiner tree. So we are interested in set cover for many reasons. That is related to, because my own concern I've written a list of problems that are really occur, such as mean cut, max cut, which is a dual of mean sum K clustering for K is equal to 2. Some problems such as mean ST cut, multivariate cut, K cut, sparse cut, many sparse cuts, tree packing, Steiner spanning, group Steiner tree correlation clustering, locally sensitive discriminant analysis, semi-supervised learning based on harmonic functions, maximum planar subgraph, online Steiner tree and competitive analysis, and other problems in machine learning. So these are the problems that I really occur. So that's why problems such as vertex cover is very important for me. So problems such as set cover is very important for me. And we will see how we can solve these problems, some of these problems, without even use those LP or STP packages of Python. And we don't even use optimization, because when you are doing some optimization, it means that you don't know the combinatorial structure of that, and you want the computer to do all those stuff. You don't want to think about it because you just want to solve it. And then do some randomized rounding to get an integral solution and those classical approaches. But nowadays, we can ask something more. We can create some combinatorial structures such that the problems becomes easier, even easier to use those LP or STP approaches. So there are many different paradigms that we can use. So, for example, the first, you could use LP or STP relaxation over even hierarchies of those LP, such as Lasser hierarchy and other hierarchies, extensions. Or you could use purely combinatorial. Or you could use the primal dual approach. Things like submodular maximization and those things. And so it all depends on the paradigm that you are using. Also, there are other paradigms in discrete mathematics that many people in computer science are not aware of, because it is in the probability community or in the combinatorics community. And so we have to talk